introduction, Robert. Hi everyone, I'm Ritvik. I'll be talking about our work on optimizing Ancilla-Based in the prime factorization or simulating some quantum material through a Hamiltonian and so on. Today, various new hardware architectures are being developed for implementing these quantum programs on a real hardware. The most common way to program Oh, okay. Hi, is this better? Yeah. Okay. So others like Tower and Spire can kind of provide you features like that are very familiar to programming language people, like control flow in quantum programming. And others like SilQ can kind of provide you features for both. Overall, these languages make programming easier and way more scalable, but they come with their own drawbacks. Their modular abstractions can sometimes lead to inefficient circuit design. That's where Spire comes in. It's a tool for compiler-generated circuits and leverages the abstractions present in these languages to optimize these circuits further. So let's walk through two language examples to see what we'll be dealing with in this presentation. First, we have Unqomp. It's a more circuit-level-like language, which can be used to describe quantum programs. And we have an example of an adder operation here and the corresponding circuit on the right for n equals to 2. Starting off, Unqomp allows you to have different types of qubits. You can have data qubits that start and end in an unknown quantum state because they're basically storing the variables of the program. And others are ancilla qubits. They start and end in a known quantum state, most frequently the 0 state, so they can be used to store temporary variables, just to make your computation more efficient and easier to perform in the restricted resources we have. In Unqomp, programmer manually writes out parts of the circuit, like the compute gates, that store some temporary result on your ancillas, and the transform gates that use those temporary results to change the quantum state around. Now, unlike a classical program, you can't just get rid of those temporary results that you created. What you need to do is you need to carefully unentangle them from the rest of the qubits, and one way to do that is uncomputation. Unqomp allows you features to just call circuit with uncomputation, where the compiler would go in and directly instantiate and synthesize these uncompute gates for you, creating this compute transform uncompute pattern. Now we can look at circuits from control flow languages as well. Tower is one such language. It basically allows you to write code that looks like classical code, but deals with quantum variables. And we can compile this to a circuit with compilers like Spire, which is particularly focused on Tower. In this compilation process, control statements basically become controls on your quantum circuit. And any temporary variable assignment can be handled by the with block, which allows you to instantiate temporary results, which are used inside the do block for your computation, and then undone. Just for explicitness, I've added the undo block there. And you can pattern match what block corresponds to which part of the circuit here. So this is the same pattern we saw in Unqomp as well. We call it compute transform uncompute, or CTU for short. One thing we note is that the compiled circuit is sometimes very inefficient, and you can see that by just taking the Tower circuit we were seeing and like a more efficient implementation just on the right, which can be done by just very simple rewrites. So one thing we do note there is, luckily, these compiled circuits have a lot of features that can be exploited for optimization. First of all, they have these repeated CTU patterns that come up multiple times in the circuit, and they have a lot of qubits that are either ancillas. They start and end in a known quantum state, like the state 0, shown highlighted here in yellow, or output qubits, which start off as an ancilla, but they're not uncomputed, so they're unknown at the end. So those are highlighted all in yellow for all the regions that are subsetted to a known quantum state. We build optimization tools by basically building rewrites that leverage these two pieces of information to optimize circuits like these. We'll work with the adder circuit example that we wanted to, and we'll extract the CTU pattern out of it. You have the compute gates here on the left and the uncompute gates on the right. The corresponding pairs match each other in color, so you can see that. And the transform gate is right here in the middle. Starting off, we see that the compute gates compute some result, uncompute gates undo that result, but the temporary gate right there in the transform gate right there in the middle uses that result during the course of the circuit. Thus, it creates a dependency between the compute-uncompute pair. One way to resolve that dependency is to check all the possible cases for which the transform gate can be applied. This can be done by just taking a qubit that it is not active on, that is operated on by the compute-uncompute gates, and simply enumerating the two possible cases you can have 0 and 1. I can keep doing, and these gates have mutually exclusive controls, so only one of them will be applied, given a quantum state for A0. And you can keep doing that to end up in a 2 to the power n replicates if you expand onto n qubits. Once you've done this, I promise you, you can move the compute gates all the way to uncompute gates, which allows you to go further in your optimization process. The way this works is there are a bunch of cases where control conditions don't match, which means they're applied mutually exclusively on the circuit and can simply be swapped. And you can keep doing that until you end up in a scenario where control conditions of the compute gate are a strict subset of your replicate. Now, you can still perform the swap, but you need to preserve the action of the compute gate on its target, which can be done by simply just swapping the control around, in this case, because it's just an X gate. And I can keep doing that until all the way till I have my compute-uncompute pair near each other. I can do the same thing for the other compute gate, changing two replicates in the process, getting this circuit here. Now, once these swaps are done, I can merge these compute-uncompute gates together, resulting in a circuit with just the replicates. To further optimize this circuit, we find that there are a lot of cases where we are just enumerating the same gate for two possible control conditions. I can merge them back in an action sort of inverse of the expansion that we saw earlier, and get a circuit which just skips that control. You can keep doing that further until we end up in this circuit which just has multiple mismatches. Now, moving on, with all the basic rewrites we've discussed up till now, right here on the left, we can't actually optimize that circuit further. One thing we can do is combine them together to build larger circuit transforms that can allow you to move forward in the optimization process. One way that works is, in the case of these multiple mismatches, we can convert them into a new CTU pattern in the circuit by just adding and deleting some gates and using the basic rewrites we had right now. We can keep doing that further, and we have now a circuit with two CTU pairs. Nicely enough, using all the basic rewrites, we can merge CTU patterns together as well, resulting in a circuit which just has one CTU pattern that's hopefully better than the one you started off with for optimization. These two circuit transforms that we just discussed generate new CTU patterns that can then be leveraged later on during the compilation process for further optimization as well, once you see all other targets. These rewrites are correct, and the way to check the correctness of these rewrites is to just check the unitary applied by the original and the transformed circuit, and if the difference between those unitaries is simply 0, equality is preserved. This is a standard definition you guys might have seen before, and it just means that the circuit is equal for all input states for all qubits. One thing that doesn't catch is ancillas. Ancillas are kind of special. They are restricted to a special state, the 0 state, on its interface. And starting with the circuit with the multiple mismatches, you can see that there are a bunch of cases where control conditions are never satisfied, like control on state 1, and the highlighted portion is all restricted to state 0, and trivial controls that are on state 0. That results in a final circuit that has just one Toffoli gate, which is this rewrite is only correct assuming ancillas are correctly used. This means that we can now formalize this equality for these kind of rewrites as this type 2 equality right here, where if qubit I is subsetted to 0 state in this ket notation, and the delta U admits this bracket term, we don't need to get into the details of what this means right now, but just mean that the difference between the unitaries only shows up if qubit I was in one state, which is just not possible if it was correctly initialized. Moving on, we can walk through one simple proof. We have the gate deletion rewrite that deletes this gate if it was controlled on state 1 and it's subsetted to state 0 on its interface. And here's the unitary shown here on the right in tensor product notation. The only reason we want this notation is that it's pretty easy to make it symbolic and extendable, where each control becomes its own bracket term. And you can then club terms together, show final unitary, and since this just deletes the gate entirely, the transformed unitary is simply identity, and the difference matches the type 2 definition that we started with. For more details, please just look in the paper of how this rewrite is proven, and all others are proven as well. This is the overall flow that we are working with. We can now move on to our compiler implementation that does this optimization called Spire. Spire takes compiler-generated circuits from Spire, which is the compiler for Tower, and Unqomp-generated circuits. And the way it works, it first comes with custom frontends that modifies the input, the circuit from these languages to be lowered only onto the Spire IR. And it tracks the ancilla information from the original circuit to correctly annotate the Spire IR at the interfaces to know which things are ancillas where, which you can then use to basically have your circuit in the Spire IR, which has multi-controlled single target gates. And we use ancilla state propagation to just sort of push that information where the qubit is restricted to special states around. The rewriter comes with various optimizations, like it applies those rewrites speculatively. It caches the CPU targets it has already seen. It applies the full expansion to 2 to the power n replicates for only smaller CPU pairs, which span fewer qubits, and uses a more direct optimized rewrite flow for larger CPU patterns. And it comes with various popular lowering optimizations that previously people have worked on when it comes to uncomputation as well. So if we evaluated Spire on these Tower and Unqomp generated circuits, range spanning a few qubits to hundreds of qubits, and circuits which span from tens of gates to thousands of gates, and in some of our ablation studies, tens of thousands of gates as well. We optimize these circuits for across these 4 metrics for qubit count, 2-qubit gate count, etc. And we just report our numbers in the next slide in this percentage improvement formula. Don't need to get into the details, it's just like what is the percentage improvement relative to the original implementation. We compare against various other circuit optimization tools that are out there. And we find that Spire generally improves upon all metrics for all the benchmarks we were evaluating for. These are just a subset from the paper here. And there are more in the paper. You see all the negative percentage changes is just like how much what percentage amount we were able to reduce the original circuit. And there are some cases where we are slightly worse on one of the metrics to get an overall improvement on all the others. In comparison, we find that other circuit optimization tools are generally much worse. For example, Quartz can't even scale to the larger scale problems we are dealing with. And others like Feynman and PyZX are often limited by the fact that they can't deal with the lowering optimizations that these compilers often use, and hence are sometimes limited on what kinds of optimizations they can use, and are not aware of these structures anyway in comparison to Spire. Here, just like the average numbers, I've reported it out there just to see what that reduction looks like. Stepping back, one thing we wanted to check, though, from this overall work was, could we just not have implemented these rewrites as a higher-level program transformation? What's the difference between those two? One thing we found is that these gate-level rewrites, in some cases, yes, do have corollaries to higher-level program transformations. Some, like the ancilla state propagation that we were doing to annotate the ancilla qubits around, is basically similar to constant propagation in a compiler. Or the single mismatch merge that we were doing, which merges gates and deletes a couple of controls around, deletes a gate and deletes a control, is basically a form of conditional fusion that we are doing right there. But that's not the case for all gate-level rewrites, because there are a bunch of gate-level rewrites that are really hard to express in the higher-level program language. The ones we found really tricky to do and still haven't been able to figure out properly is the merging of the CTU patterns together, or merging these multiple mismatch gates together, because it just results in patterns that you generally don't see in those higher-level languages, or they just don't support it easily. These CTU patterns and ancillas, while are visible in the program level, like with the with, do, undo block that we've been seeing multiple times in this presentation, that's not the case for all of these patterns. That's because some of these conditional statements, for example, can get lowered to its own CTU pair on lowering. And that's just not visible in the higher level program as easily. And there are a bunch of arithmetic operations, etc., that have the same features in Tower, for example. We find that the program level rewrites, if you apply them, can also hurt optimization on the gate level. And the main example we saw was mainly with Spire, which is the compiler for Tower again, which comes with a bunch of which comes with a couple of program level transformations. And in one or two cases, I think we saw that overall, applying all of those rewrites actually results in a worse circuit than when none of the rewrites were performed in the first place. And that can be just basically seen by depth, in the depth of the circuit after Spire is applied onto the circuit generated from the Spire compilation process for the same Tower program. There are more cases in the paper of the overall ablation studies that we were playing around with. Overall, we find that these compiler abstractions can create sources of inefficiencies in the circuit design or the final program you're going to be working with. Our compiler uses or targets these CTU patterns and ancillas in particular to bridge the gap between higher level program abstractions and gate level rewriting tools that have already existed for a while now. And overall, from this work, my main takeaway was that understanding the consequences of these abstraction choices that we are making is really useful. And as we have discussed in the paper, there's probably a lot more optimization opportunities that can be found by understanding what those abstractions lead to and how can we exploit them to find more optimization opportunities, and what's the trade-off for applying these rewriting optimizations between the higher level program, in the middle somewhere, or on the gate level as we are working with, or even further down on the decomposed gate level of the final circuit. Thank you.
Thank you, Ritvik. People can step up to the mic with any questions.
Hi, Sébastien Bardin from Sara. I was wondering, in your comparison, I didn't see, did you check against optimization from Qiskit, typically?
Good. That's a good question. So one thing we had to contend with was, depending on these circuits that we were dealing with, some of these can be compiled to simply Clifford plus T pretty easily. And if you just throw Qiskit at it, and if you apply even the smallest level of optimization, it will convert everything to U3 gates. And suddenly you're not dealing with the same gate set in the first place. So that was one of the main issues when dealing with Qiskit itself, where it just converts. It is really good in taking any Toffoli implementation and just finding, oh, these are places I can plug U3s in and make it much more smaller. But that's a problem that we sort of don't want to sort of tangle with, mainly because we believe that Spire can be applied at a higher level anyway, above Qiskit, for example, where you can then, if you actually did want to use U3 gates and so on, you can just apply the Qiskit backend stuff once those once the circuits have been optimized. And just a quick note, the lowering optimizations that we're dealing with are very specific to this uncomputation pattern, and it's not something that, unless you're aware that this is a compute-uncompute gate, you can't really do that even at the lower gate level. And that was another thing that was basically missing from Qiskit.
Okay, thank you.
So I have a question.
Yeah.
So this Spire IR, it sounds like it's pretty low level. Is it just like a circuit language with multiply controlled X's, or is there more going on there?
Okay. So that's a good question as well. So our IR that we wanted to work with, it is fairly low level. The way it works is you just have not necessarily multi-controlled Toffoli gates, but any kind of multi-controlled gates. And I'm trying to skip to the slide and I ended up going the wrong direction. Here. So all of our circuits are expressed as these multi-controlled single target gates in our lowering. And that was just mainly because it was much easier for us to reason about, oh, these gates commute, or these gates change one of the controls in this pattern, and so on. I mean, it would be useful to explore higher level IRs as well to see how that would work. And but yeah, finally, I think if you have any multi-control gate, what we ideally want is as high level representation of that multi-control gate, because often compiler tools would even decompose that down to some multi-control gates that use some ancilla, and then you need to lift that information.
And that's an issue for Feynman, the Feynman tool as well, I believe, because they have this MCX routine that they can do. So were you able to provide sort of intermediate circuits to Feynman so to see whether it was able to optimize away the multiply controlled X's?
Yes. So the way we evaluated this was basically then for these circuits, we generate this. Once we are generating these circuits from such compilers, we make sure that they're as high level multi-control gates as we can get from these compilers, and then use the same circuit for Spire as well as Spire as well as Feynman. And we basically use the multi-control Toffoli decomposition, and we found that does obviously give you a large performance improvements, and that's why Feynman was one of the much better performing tools that we found when we were comparing all other benchmarks against Spire.
I see. All right, very cool. Thank you.